All right, let's just dive right into this blueprint. Today, we're tackling one of the most gritty, awe-inspiring feats in modern infrastructure, building massive bridges over deep, churning rivers. Welcome to today's Explainer. We're looking at a process that is quite literally defined by the smell of diesel exhaust, the deafening grind of heavy steel, and a relentless day-in, day-out fight against nature. You know, when you see a massive suspension bridge stretching across a huge waterway, you're looking at the final polished result. But getting there, it requires pulling off an absolute structural miracle in what is easily one of the most hostile work environments on the planet.
It all really starts with one fundamental question, right? How do you actually build on water? Because in this scenario, the river isn't just a nice backdrop. It's a deep, fast-moving antagonist. It is constantly trying to wash our efforts away, scour the riverbed, and push against our materials with thousands of pounds of hydrostatic pressure. So that leaves us with the ultimate engineering puzzle. How on earth do we construct a heavy, permanent foundation in a fluid, totally dynamic, and downright chaotic environment?
So, here's our blueprint for today. 1. The Deep River Challenge. 2. Blueprinting the impossible. 3. Securing the underwater foundation. 4. Rising above the water. 5. Spanning the Great Divide. And finally, number 6, the final connection.
Let's jump straight into part 1, the Deep River Challenge. Now, building a skyscraper on solid Earth is certainly tough, no doubt about it. But it's predictable. You have stable, load-bearing dirt and dry conditions. But a deep river, that's a whole different beast. You're fighting immense hydrostatic pressure, shifting riverbed mud that offers absolutely zero structural support, and constant churning water flows that actively fight against every single ton of steel we drop into it. I mean, you can't just pour concrete into a rushing river, right? It would literally wash away in seconds. So we really have to outsmart the fluid dynamics here.
Which brings us to phase 2, blueprinting this impossible. Take a look at how we actually schedule this counterattack against the forces of nature. The underwater anchoring phase alone, that takes up nearly half a year, sometimes way more. The most agonizing, incredibly slow, and highly dangerous work happens entirely out of sight, deep underwater in the freezing muck, long before a single pillar even breaches the surface. It is literally months of unseen, gritty labor just to get ourselves to ground zero. Moving on to step 3, securing the underwater foundation. The logic here is pretty simple, even if the execution is brutal. If we can't build in the water, we have to eradicate it. It's an intense 3-step loop. First, we aggressively drive temporary walls deep down into the riverbed. Second, we pump millions of gallons of that churning water out through massive dewatering systems. And third, we pour just unbelievable amounts of concrete into the newly created void. This exact sequence allows us to temporarily shove the river aside, creating a dry, workable construction site right smack in the middle of a rushing current. First up in our toolkit is the cofferdam. Think of it as a giant interlocking steel fortress. Massive pile drivers, echoing with these earth-shaking rhythmic thuds, hammer corrugated sheet piling deep into the river's mud. Once that's totally closed off, the water gets pumped out. This fortress protects our heavy machinery and, more importantly, our crews from the crushing hydrostatic pressure outside. Imagine standing at the bottom of a cofferdam. You're surrounded by the smell of damp earth. You look up and you see a wall of cold steel holding back a literal river just inches away. It is engineering at its absolute most visceral. But what happens when the river is simply too deep or the mud is way too thick for a cofferdam? Well, then we rely on a caisson. This thing acts like a massive pressurized diving bell made of reinforced concrete or steel. Workers literally have to excavate the mud from the inside of the bottom of the box. Now, historically, doing this under high atmospheric pressure meant risking decompression sickness, the bends. And honestly, today it still remains highly dangerous work. As crews dig out the mud in the damp, claustrophobic dark, the sheer weight of the caisson causes it to sink, just inch by agonizing inch into the earth, until it finally hits solid bedrock. Once it finally hits rock, that hollow inside is completely filled with concrete. And guys, we are talking about pouring upwards of 10,000 plus tons into these caissons or cofferdams. Picture fleets of cement mixers and barges idling under glaring floodlights, filling the night air with the smell of wet concrete and heavy diesel exhaust. They have to work around the clock in a continuous pour, because if the pour stops for too long, a cold joint forms, and that completely ruins the structural integrity. And since concrete curing is an exothermic reaction, this massive block generates an incredible amount of heat as it hardens, finally forming an immovable anchor against the river. Okay, section 4, rising above the water. As that concrete base finally breaches the waterline, the whole atmosphere of the site totally transforms. The air just fills with the deafening roar of heavy machinery, the sharp smell of ozone, and the loud crackle of arc welders. You've got massive cranes mounted on floating barges maneuvering multi-ton sections of steel straight through the sky. You hear the systematic riveting and welding. You see showers of sparks falling toward the water, all as the bridge's vertical spine finally emerges. We are securing the massive load-bearing piers that are going to eventually hold the entire weight of the roadway.
Now for part 5, spanning the Great Divide.
Connecting these isolated towers across vast stretches of open air, that requires an absolute masterclass in material logistics. High-tensile steel suspension cables are spun, strand by strand, perfectly designed to take massive tension and distribute the bridge's weight back down to the towers. Right below that, heavy reinforced steel girders are hoisted directly from bobbing barges into place. And finally, the decking, made of poured concrete, provides that solid commuting surface. Every single piece of high-tensile steel and concrete relies on the component next to it, transferring the immense weight of the span back down, straight through the towers, and right into those underwater anchors we fought so incredibly hard to build.
Which brings us to our final section, the final connection.
After months, sometimes even years, of fighting the river, fighting the thick mud, and fighting gravity itself, the final pieces of decking are locked into place. But here's the craziest part. The absolute hardest part of the engineering is completely invisible to the daily commuter. Thousands of cars and heavy trucks drive over these magnificent structures every single day, right? We just look at the soaring towers and the beautiful cables catching the sunlight. But the true, gritty, dangerous triumphs, the massive cofferdams, the sunken caissons, the 10,000 tons of concrete locked deep into the earth, they remain entirely hidden beneath the churning water. So next time you drive over a deep river, look down at that dark water and ask yourself, do you actually know what's holding you up? Thanks for joining me on this explainer. I'll see you on the next one.